I guess there are two foreigners, but let me excuse. So most of the talk I will speak in English, but sometimes I will talk in Korean. So let me excuse this. Okay, so today I choose a rather different topic. Usually I talk about some surface, deformation of some singularity in surface, but today I choose a different topic, which is called GIT. Okay, so I guess most of the audience are students, so let me start by quite elementary examples. So now I'd like to parameterize points in P1. So we want to parameterize this 4 point. It can be distinct 4 point, maybe some you have maybe some double point or something like that. So then if you consider this one as a roots of the polynomial, so then this corresponding to homogeneous equation of degree 4 with two variables x0, x1. So then if we're writing the whole homogeneous equation of degree 4, so then A0 x1, 4. But now interesting to the corresponding solution of this equation. So if you multiply, then still we have the same solution. So it implies that this A0, we are interesting to the point these points are in P4. Okay, so we are interesting basically the 4 points in P4, which are coming from this coefficients of the homogeneous equation of degree 4. But then there is action in this P1 is we can consider this SL2 action on P1. But then this action induced the action here. So we have action in this SL2 action on P4. So now say this is G. But then in this action, we have some bad point. So there are some bad points in P4. So for example, if you consider this action, this one parameter subgroup acting to present this point, so then this goes to something like this. So and then if you consider this limit of this C-star action, so then this 0 points this. Yeah?
Your underlying field is complex numbers?
Yes. So maybe now I'm just interested in complex field. Yes. We can do also the field with the positive characteristic, but then we should be a little bit careful. But here, let me do just over C, or just characteristic 0. Okay, so then these 0 points are some disclosure. So basically, what we want to do is that now we have a P4 and we have actions, and then we want to considering this quotient. But if the 0 is in the OB closure, then you cannot make a quotient. So this kind of point should be removed when we do quotient. So then that is why this point is a bad point. But then similarly, if you consider whole 4 point, so then there are distinct 4 points, or multiplicity 2 here, and then 2 point, or multiplicity 2, 2, and then also possibilities multiplicity 3, and then multiplicity 4. So for example, this case, and then do a similar action to here, then also you get the 0 is still there. So this is a bad point. So this is called the unstable point. And then, but here, this is a good point. You cannot make this kind of situation. So 0 is not a closure. But for example, if you're looking at these 2 points, so this is a good point anyway. So this is called the semi-stable point. But there are difference between these two. So in this case, now you fix this multiplicity 2 point, and then fixing here, and then moving this point. So you can do this. So this, so that means that these points are closure, also OB closure over these points. Okay. So these points are good point, but the difference is that these points are coming from this OB closure. These are called the strictly semi-stable point. And this good point is called the stable point. Okay, so then if you do the P4 minus this bad point, and then quotient by this given this SL, here I denote not just one I denote these two. The reason is that we have this strictly semi-stable point. So then these are in fact the P1. Okay, so then let me give other interpretation of this 4 point. So here we consider per point directly, but using some curve. So now we have a P1 with a 4 point here. If you have a distinct 4 point, so then you can make a double cover over this P1, or if you are more familiar, then say just a sphere. So now we have some curve branched to this 4 point. So then something here, but then you can compute their topological number. But then this is a sphere. So it's just 2 times 2, and then we have 4 points. Branch means the inverse image of these points are 2 points, but something like this. So picture looks like. So here we have a branch, also branch here. So 2 branch, 3 branch, and 4. Okay. So then this above one is 2, 2 minus 4, so it's 0. So topological number is 0, so this should be the torus. Elliptic curve. And then also you can make the what's the this double curve over this kind of point. So for example, if you're looking at this case, so then what's the above one is the just double curve. Here is the nodal. So this. So that means that sending this point to here, then is singular point. That makes this. And actually, you can get what kind of singularity here is simply that this is now you give a coordinate here, and you give a new coordinate here, and this is a double cover. So y square is x square. So the singularity is this type. So this is the picture of the double curve over here. And then how about this one? So what's the picture of over one is simply so 2p1 meeting 2 point. So for example, conic with the line gives us a double curve of this. And then 3-1 case, also you have a double here, but here picture looks like this, because here should be y square equal x cubic. And then also you can do this one. So this kind of the degeneration of this torus, elliptic curve. So then considering this torus as a cubic curve in P2, so then we can also consider this one as considering the all cubic curve in plane. So considering the all cubic, so these cubic curves in P2. But then also there are some bad points. For example, 3 times of line, this kind of points are bad point. So then, and then considering this projective space, so then it's P9 and then minus some bad point. And then, but now here SL2, but here now in P2, so then quotient by SL3. So then this is also P1. Okay, so now I gave 2 constructions of this parameterizing by, but not just parameterizing, quotient by isomorphism class coming from this quotient by SL2, in that case SL3. And then now we see that their space P1. So here we subtract some bad point, but y is, for example, P4 previous, this P4 minus bad points is compact. I mean, we know this is now P1, but why this? Because these are not compact set, P4 minus some bad point, but then when we do quotient, then why these are compact? So what's the reason for this? So for example, consider the x04 plus t x14, considering this family, and the t is the small disk. So this small disk in C. So parameterizing by this t. So then if t equals 0, then we get the bad point, right? So if, for example, if you're writing this equal u, so then something like now u is here and the u is not compact, so something like here, and now that t goes to here, then we have a bad point here, and then that family is moving something like this in u. we cannot quotient directly here because this going bad point. So we should replace. So how can we replace this one by using this group actions? So for example, you have S4 equal T. So then this goes to, so then this equation can be changing to okay, so this changing to this, right? And then say also let S equal S bar square. So then now considering this action, so these are in SL2. By these actions, so then this goes to then we have then S, for example, if you're looking at this equation, then S bar x0 plus S bar x1 by these actions. So then after this action, this changing to, so consider this action. So then this goes to the S4, S bar 4, and then x0 plus x1. Okay, so then this, I mean, it's nice because always distinct 4 point. So what I said is that now we have this by parameterizing by T then goes to bad point, but after some group actions, so then you can changing this to some good point. So by these actions. So this is called the semi-stable replacement theorem. So above space, this is not compact, and it can be go to bad point. But after moving by group action, you can only consider inside of a semi-stable locus. So then quotient makes compact. That is the why. So that gives this space is compact. So to using this kind of idea, if you have some parameter space, some group actions, and then if you have this kind of semi-replacement theorem, then we can make a compact space by this quotient. And then also we can understand the different way of the in this example. So let me explain some geometric understanding. So again, this example again. So then, so here we have a family. So if t equals 1, 0, then we have a 4 point. But then if t equals 0, then we have a quadruple point. And then, so it looks like picture. It's like go to this, 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 right? So these 4 points are moving by moving over this P1. But then, so this is P1, but if you consider this total space is the surface, and then now you blow up to this point. So blow up is now this curve, and then they separate the tangent direction. So blow up to this point, then we have this, this. So then here is t equal outside, and then goes to this. Because the blue one makes the separate the tangent. So if this so now these four four curve, their tangent directions are different, and then it makes a separate. So that is the why we separate the 4 point to here, and then blow down over this point, and that gives us this trivial family. Because actually you can see the does not depend on the S bar, because they're always the same 4 point, right? So that is the reason. So we can understand also by this geometric way of these examples. Okay, so then this theory is, so generalization of this kind of example is called the geometric invariant theory. It's GIT. Okay, so original geometric invariant theory is coming from the invariant theory, or now called the classical invariant theory. So this theory was very popular in the 19th century. But then the theory was rather dead in the middle of 20th century, but then now it's going popular again. So what's one of the important problem in invariant theory is the following. So considering this polynomial ring, just consider polynomial ring, and then considering some group, and then was then looking at the invariant ring by this group. So then question is that when this invariant ring is again finitely generated C algebra. And also, and if it is finitely generated, then what are the generators? This is one of the most important problem in the invariant theory. And then, for example, there is Hilbert famous theorem of the Null-Stellan-Jacques, and also CGG theorem, and this basis theorems are actually related with these problems. So then, and then also one can generalize to not just the polynomial ring. So these are the famous Hilbert 14th problem. Was if R is finitely generated K algebra, K is some field, and then RG is also finitely generated K algebra. So these are the questions. This looks rather purely algebraic questions, but it's quite hard to answer in the some difficult groups. So then, if the G is a reductive group, then it is true. So then, I mean, reductive group contains this SL, GL, finite groups, these kind of groups. But there is a counterexample. First counterexample was done by Nagata in the 1950s. And then after that also there are many works done for these problems. And then also people are interested to the G equal finite group. Also there are many studies G is finite group. So then one important paper was done by Stanley. So in that case, he proved that this invariant ring has some special ring structure, which is a Cohen-Macaulay ring. So in that case, this Cohen-Macaulay ring. So in the finite case, the interesting question is what's the property of this invariant ring? I mean, what's the algebraic property of this invariant ring? So, for example, the polynomial ring, when these are, for example, polynomial ring, I mean, this case classified if the group is generated by reflection group is polynomial ring. For example, if G equal symmetric group, then it's polynomial ring. And then polynomial ring implies the complete intersections. And the complete intersection implies Gorenstein ring. And Gorenstein ring implies Cohen-Macaulay ring. So in this case, Cohen-Macaulay is known. And the Gorenstein case also, if the G equal GLN subgroup, then is corresponding SL group. But this is here unknown when complete intersection. Also, there are some problems of combinatorics also related with this invariant ring. Actually, he applied this invariant theory to combinatorics. So this just I very briefly introduce some invariant, classical invariant theory. But then this. So Mumford was the first person to introduce this invariant theory to constructing moduli space. So he used this invariant theory to apply construction of a moduli space. So for example, previous P1, these 4 points, this kind of one. So this is now called GIT, geometric invariant theory. 여기까지는 쉬운 얘기를 했다고 생각하는데 So I hope most audience understand these previous examples and just this. 어떤 거요, 이거? 그러니까 아까 큐빅 컵을 어떻게 만들었냐면 P1에 아까 그 네 점만 생각했을 때 이게 가장 제너럴 포인트였잖아요. 그럼 이 P1 위에서 지금 더블 커버를 생각해요. 2 to 1. 그러니까 더블이라는 거는 각 점마다 2점씩 있는 거예요. 그러니까 지금 스피어가 있는데 스피어 2개를 붙이는 거죠. 근데 네 점에서는 붙여요. 그러면 지금 네 점에서 이 스피어의 네 점을 서로 브랜치를 시키면 얘는 사실은 토러스가 되는 거는 그냥 토포로지컬 넘버를 계산을 하면 토러스가 나오고요. 그래서 다시 아시면 뭐냐면 이거의 제너럴 포인트, 4개의 디스팅트 포인트에 해당하는 건 토러스라는 걸 아는데, 그러면 아까 이 4포인트가 예를 들면 뭐 이렇게도 될 수도 있고 뭐 이렇게 될 수도 있잖아요. 그러면 그거에 대한 대응되는 픽처들을 아까 보여줬고요. 그래서 근데 얘의 컴팩티피케이션이 P1이니까 지금 똑같이 토러스에 그거 대응되는 것도 P1이라고 예, 그 얘기를 한 거예요. 아, 이제 그 얘기는 할 거예요. 네, 이제는 좀 더 어려운 거를 정의를 해야 되는데요. GIT에 대한 제너럴 세팅을 하려면. 그래서, 일단, variety가 주어져 있고, so given a variety and the ample line bundle, so this is called the polarized variety. So then, if you some tens of this L, so then so polarized variety means that basically we want to looking at variety plus some other information, which information gives embedding X to some projective space. So for example, I mean cubic curve you can consider cubic curve as a P2. Also, you can consider this 4-point in P1, something like so. If you have so now you have an object, and then you're embedding that to some big projective space. So now we have a embedding here. And then, but then now I want to parameterize this X inside of this big projective space. So then. Looking at the Hilbert polynomial, so yeah, I will not explain the details of this. Was the shift cohomology, but anyway, so this L R is same as H0 if R is sufficiently large now. Okay, so if sufficiently large, then this gives us embedding, so it means the very ample. So very ample implies no other cohomology except zero cohomology. So then we have this one. Okay, so then now H0 LR. So now say this is PR. So then we have isomorphism this to the some fixed vector space. Okay, PR. So basically we want to fix some plane. Okay, so something like now we have this big projective space, and we now X is right there. So this X is right there, and then we have a frame in this coming from the vector space. Then considering this okay, so for example so something like in the P2, for example, if you consider this is 3, so then you have L equal, for example, line. So then this cubic equation and then symmetry power. So then there is a natural map from K symmetry power to this KR, degree KR, this equation. So then we have a kernel here. And then this kernel induced the closed subscheme. So what I want to discuss here, the reason, so in the previous P1 case we have a 4-point. So that case, easy to see what's the parameterized family. So now here we have a 1x, And then question is how to parameterize the x. So now we want to parameterize this x inside of the Grassmannian. So we're collecting the x so inside of Grassmannian. So that is determined by this kernel. So then curse subscheme of Grassmannian coming from this. So SK, and then we have isomorphism here. So C, PR to this one. So that is now PKR. Okay. So then, X, LR, and this isomorphism gives a point in this Grassmannian. Okay, we have some family, and then now invading X is here. Then we have SL actions coming from this embedded one. So then this SL acting here. Okay, so something like in the previous example, this looks like P4, and now we have SL2 acting there. So then we have to determine which one is bad point, and then which has a semi-stable point, and then considering the quotient. So then how to determine which points are good, which points are bad. So how to determine the good point, bad point. So after this action, then we need to determine stable, semi-stable, unstable points. But still I didn't define which one is stable and semi-stable or unstable. So what's the general definition of a stable, semi-stable, unstable point? So now let me define these notions of a stable, semi-stable, and unstable point. Okay, so now we have this X at R, and we have this action there, group actions. So then there is a Hilbert-Mumford criterion. Is if you wanted to determine this kind of one, it is enough to looking at the all one-parameter subgroup. One-parameter subgroup means in this case just the C star. So looking at the C star actions, so then we have this C star. So actually these actions are in the Grassmannian. So now this is just 1 point in the Grassmannian. So then now acting this X, and then these curves are moving by C star because you have actions, so you're moving. But then there is a limit because you can go to C, right? So there is a limit. So we can make by this action, then, so this one parameter subgroup of this. But now when changing to SL to GL, actually, then we will normalize later. So then GR PR. Okay. So that coming from the N. So we have this one parameter subgroup gives test configuration. So XR. So now we have some over C. So these are coming from these actions. This proper flat family. And here C star. is simply so here we restrict to C star, but in the general part, except the t equals 0 is by just moving C star, so it's same one, so we can get this xt, and then, but also this equation line is also moving, so here also we have L, so then xt is simply isomorphic to xlr if t is non-zero. So outside is simply the same one because of C star. And then, so we have a flat family here, and the outside is same, but and then also we have a C star action here. So this family is actually equivalent by the C star actions. Okay, so here we have an equivalent L ample line bundle L on X. Okay. So one family gives us this family, and the general fiber is same, but the central fiber is the limit. And then now we have this sister action, but this is an abelian group. So here we have at least each fiber we have a frame. So it means that we have some rise on some vector space, and we have abelian group action. So then you can diagonalize. So then you can consider their weight because from the diagonalization. So then. So then we have this weight function. This weight function. So basically coming from these eigenvalues of the diagonalization, weight function on L restricts on the K and then pi plus tau. X and 0. Okay, so this. So this is simply the H0 LK T H0 LK. Okay, so we have a weight function, this by induced by C star action. And then increasing this K. So now we have a function, weight function, and increasing K. And then this function can be written as a polynomial with K. So then this is a polynomial of degree n plus 1. So n is the dimension in K, KR. So we have a weight function with a polynomial of degree n plus 1. And then defining this, let's see, RK. So this is normalized weight. Because why we consider normalized weight? Because previously we considered SL, but now here we consider GL. So changing to GL to SL, you have to make a determinant equal 1. So that makes a normalized weight. So that is the omega, that is WK, and then RPR. So this is a Hilbert polynomial minus PK. And then just express this function as, because this is also polynomial of degree n, so we written this polynomial. So then something like RKI and I equals 0 to n plus 1 polynomial. So we have some polynomial here. And then, in fact, this each coefficient is also polynomial. So this is also polynomial of degree n plus 1 in R variable also. Okay. So basically we have some polynomial coming from the weight, and each coefficients are also some polynomials. So then we define the stability and this unstable by just that polynomial. So then just define the, okay, so this is also polynomial. So then using this normalized weight, so then, so let me write again too. So then this EIR is also polynomial. So say EIJ, RJ, and J equals 0 to n plus 1. So then from the normalized weight, E n plus 1 is 0 coming from the normalized weight. So then what's the definition of stable? So Hilbert stable with respect to R is the if this weight polynomial is positive. So what's the bad point in the P1 case 4 point? Bad point is the zeros in the OB closure. So something like if you are positive, then you cannot go to 0. So this is kind of the idea, okay? Because the bad point means the 0 is in the OB closure, but if the weight polynomial is positive, you cannot go to 0. So that one is positive. And the semi-stable means this is non-negative. Okay, so that is Hilbert stable, definition of Hilbert stable. And the asymptotic Hilbert stable means the, so in this case, this depends on this R. But the asymptotic Hilbert stable means that this is true when R is sufficiently large. So here stable if omega rk is, so in this case, asymptotic Hilbert state means the, okay, so if for all R is sufficiently large, so then this one is true. So then omega rk is positive for all k who are non-negative, then it's called asymptotic stable. So it's it means the Hilbert stable when R is sufficiently large, and the semi-stable means that is non-negative. Here. And then Chow stable means also respect to R. So this looking at only the top coefficient of this one. So that so we have this weight polynomial is this one, and then looking at the top one. So if En plus 1 R is positive, goes to 4k, and the semi-stable means this non-negative, and then also we can define the asymptotic Chow stable. It's just the same way. I mean, for all R sufficiently large, and then this one is positive. Also, we can define asymptotic Chow semi-stable. Also, we can define, and then finally, also we can define what's the KAIST table. But then we have also this coefficient coefficients are polynomial of R. So then looking at again the top coefficient of this polynomial, but the top one is 0, but then looking at the next one, so this case, stable means that if for all R equals sufficiently large, the leading coefficient of En n plus 1 is positive of En plus 1 R. Okay, and then also define K semi-stable is non-negative. So basically all definitions, these definitions are coming from the GIT. And the Hilbert case looking at the whole polynomial, and the Chow is the top coefficient, and the K symptom is the top coefficient of the coefficient. And this one is called the Donaldson-Futake invariant. So they are differential geometry, but why their names are coming in this algebraic geometry, I will explain later. There is some big conjecture related with this.
Why do you call it two-stages?
Actually, these are related with the existence of Kerr-Einstein matrix. So it's something like Galabi conjecture and something related with this. So that is why I called the Donaldson-Futake invariant. So in this definition, these definitions are coming from GIT. But the final one does not relate with the GIT. So what's the meaning of related with the GIT, not related with GIT? So in this case, we have a semi-stable replacement theorem. So it means that if you're collecting the semi-stable point, Chow or Hilbert, and then quotient, give a circumfectified moduli space. But K-stability does not have a semi-stable replacement theorem. So it does not relate with this group actions directly. I mean, it's coming from the definitions, but does not have this GIT theorem.
By the way, if we have moduli space by using such GIT, is it always compact?
Yes. So maybe I have to remark. So GIT is a very strong theory to construct a compactified moduli space. But it's very hard to find what's the modular interpretation means, what are the objects inside of this moduli space. Except moduli of curve, moduli of vector bundles, they are very succeed too, but other case, GIT, the main problem is very hard to compute this. In fact, the invariant theory, usually invariant theory is very hard to compute. That is the why it's died for several, not several years, maybe some 30 or 50 years, and then now a little bit driving because now we have a very good computer program to compute. Okay, so then from the definition, this weight leading coefficient, you can get easily some relation between this this stability. So just let me write. So, for example, asymptotic Chow stable. So top leading coefficient is positive, then polynomial is positive. So it implies Hilbert stable, and then implies clearly Hilbert semi-stable. It is stable, semi-stable, and implies Chow semi-stable. And then also looking at the K stability, then these are K, this case just the K semi-stable. Also, this is true if you delete the asymptotic. So you can delete asymptotic here. But then just true until here. Then because the K semi-stable is only defined for asymptotic, so this is also true. So there are some relations of these stabilities. So then for constructing this moduli of curves, so this case, this using the GIT construction, so maybe I will explain more details a little, just a few minutes later. But then GIT construction is the same as birational geometry construction. So previously I gave a very easy example for this case. And then we blew up, and then we finally find the trivial families. So what's the birational geometries? So in the curve case, now you're moving the curve over some small disk. So then this gives us a surface. So then we have a very good theory for surface. So then apply the birational geometry of a surface, and then you can find what is the good central fiber by using the birational geometries. So I mean, birational geometry, if birational geometry can be done for n+1 dimensional, so then you can do the moduli space of the n dimensional, because the n plus, just you considering the degeneration of n dimensional varieties give us a central fiber, and then using the good theory of birational geometry implies that you can find some nice central fiber. So then you say that this nice one is called the stable varieties. So that is how to using the birational geometry. So birational geometry implies we know how to find the good one. But the problem of birational geometry is that this already you consider only one parameter family, because you only now know how to find the central fiber. But then what happens if you consider whole family? So it's rather difficult to construct the whole families. So then you need to prove some separateness, or then after then you can go to some projective space or something like that. So it's so this one is rather only very good for one parameter, but it's rather hard to for global one. But the GIT is very good for general theory to construct the global one, but it's very hard to determine which one is good one or bad one, because the computation is too hard to compute. But fortunately, moduli of a curve case, these two constructions are coincide. 어떻게 보면 제가 얘기하고 싶은 부분 하나 더 볼 텐데요. 한 5분만 얘기할게요. Okay, so then what happened to the moduli of curves? Okay, so now considering curve with the genus is greater or equal to 2, and then first of all we want to consider polarized. So there is a natural bundle is this canonical bundle. So it's looking at their power. So considering this polarized curve by this canonical divisor. So then if this n is quite big, so n is big, so then one point to prove this Chow stable is equivalent to Berlin-Mumford stable. element for the stable means that this curve, the canonical divisor is ample, so that is needed for embedding, but important thing is the singularity is only node. So because if you have a smooth curve degenerating, and then if you're using birational geometry of a surface, always you can changing to the central fiber has only at most node. So birational geometry, these nodes are equivalent to Charles table. So that is the why two constructions coincide. So this one proved by Mumford. So then Gisker. So then first one was done by Schubert. It's not the musician. So he proved the n equals 3 case, G is greater or equal to 3. So then he proved the Charles table is equivalent to Swedo's table. So what's the definition of a Swedo's table means that here, for example, if you're looking at the elliptic curve meeting G minus 1 curve, so these are the element for the stable curve. You have only node here, but then these are not Swedo's table. So Swedo's table is that this should be replaced by cusp. So basically, Swedo's table means the replacing this is called the elliptic tail, and then replace the cusp. So then stabilities the notion of stabilities are now changing because originally here is the stable, I mean the element port, but changing to the Swedo's table. So now going smaller, so what's the philosophy here is that something like if you go smaller, so embedding dimension is projectively small, then you need to allow more singularities for the curve to say the stabilities. So then so he did not consider genus 2 case, and then I studied with Hyun, Professor Hyun in postdoc, and then we also classify G equal 2 case, and then but here still n equals 3, and then what happened, for example, n equal 2. So then is your embedding space is much smaller, then you need more bad singularity, and then Hassad and Hyun, they worked for general case, and Hyun and I worked some special case, G equals 3 case. So why working special cases? Here we usually do not need the semi-stable, strictly semi-stable one, but if you go smaller genus, you need allow the strictly semi-stable one. So then very hard question is what happened n equal 1. So embedding the curve by canonical, so then problem is the hyperelliptic goes to not the hyperelliptic curves are changing by canonical embedding. So that case is very hard because one. So and then you can maybe ask so now here we consider the embedding n equal 5, n equal 4, n equal 2, also you can say n equal 3. So then question is what are the relations of this Chow and G. So this embedded by N and the genus G curve by SL and Hilbert and G SL. So it means that what's how their geometries are changing by changing varying of N. So these are some questions, and now some cases are answered by also Hassad and Hyun, and also I also worked together with Hyun. Okay, and then maybe let me delete this part. And then so here the moduli of curve case. So varying of this embedding, and then we have a new geometric object coming from the GIT, and then now try to understand what's their relations of the geometries. So this is the one problems. And then, so then what happens if the higher dimensional? So already we know that there are some examples which coming from birational geometry are different from the GIT. So then what's the correct concept from the GIT and birational geometry? And then recently the Odaka proved this case semi-stability is good notions for corresponding birational geometries. And so that is good one, but I already mentioned these are not really related with the GIT, so maybe we need to develop the GIT theory for K semi-stability. We need this. And also, there is an important conjecture related with this one is existence of a Keller-Einstein matrix related to the K polystable. K polystable means the a little bit stronger than K semi-stable, and then existence of Keller-Einstein matrix implies K polystable, and the big conjecture is the K polystable implies the existence of Keller-Einstein matrix. So that is still unsolved problem. Yeah, let me finish. Sorry for the, yeah.